Hi, my name is Rhodes, and today I'll be talking about Power Models Restoration, an open source software framework for exploring power network restoration algorithms. First, what is grid restoration, and what is the kind of problem that we're talking about here? What we're talking about is a severe contingency restoration, where the problem is that a significant portion of the electric grid is physically damaged and needs to be repaired. The objective is to order those repairs to minimize the amount of unserved energy in the system. So this is the total load power that is not able to be delivered, as well as the amount of time that that load is not being delivered for. Take, for example, a hurricane hitting the US Gulf Coast. That hurricane comes across and it takes out some transmission lines, floods some substations, and we need to figure out in what order do we start to repair these devices in order to restore power to the network. What I want to clarify here is that this is separate and distinct from a black start scenario. In black start, while there may be some damaged devices, the assumption is that load can still be delivered in the system, but that devices need to be brought online in a specific order. In this case, we're not saying that the grid frequency is down, just that there's a significant section of the grid that has been damaged and load cannot be delivered. So this is a much longer term question of how do you prioritize and begin to order these repairs that need to be done. What makes the restoration ordering problem challenging? There are two aspects that affect the difficulty of solving a restoration ordering problem. One is the power flow that you use. Whether it's a linear DC power flow or nonlinear non-convex AC power flow, that power flow formulation is going to greatly affect the difficulty of solving the problem. The reason is because there is a copy of the network for every single topology that exists during that restoration sequencing. So before any devices are repaired, there's a power flow that needs to be satisfied, and then a single device is repaired, that power flow has to be satisfied, and the number of copies that we have is the number of different network topologies that exist during that restoration. So in most scenarios, that would be a separate network for every single repair that is done. All these topologies are linked by the previous repairs that have done, and they all have a copy of those network flow variables that exist in every single network. Essentially, more repairs means more copies of networks, and each individual network can be challenging depending on how difficult that power flow is. So we can look at these formulations that represent each network and potentially looking at algorithmic heuristics that affect how many repairs we have to consider at once, and again, how challenging that is. And a significant portion of those algorithmic heuristics is considering how many copies of the network, but also the number of mixed integer variables that represent those repair decisions to be made. I'm going to start out by talking about some of the formulations that we support in this package and the ones that are represented in the case studies. There are three of these formulations, the first of which is a linear approximation, the DC power flow. This is a linear representation. It's very fast to solve, but it makes some assumptions, and as a result, it ignores reactive power in the network. It makes assumptions about voltage being nominal, voltage angles being small, and these assumptions may not be true anymore in a very stressed network that is undergoing this restoration. We can take a look at nonlinear convex relaxations, like the second order cone representation of the power flow, and this accounts more accurately for reactive power flow, for these voltage changes in the network. It is going to be much slower to solve than that linear DC problem, and it may still be AC infeasible because it is still a relaxation of those problems, but we can find global solutions here. The nonlinear non-convex representation of those full AC power flow equations. These are accurate. These are the full physics of what's going on in the steady-state systems, but it is hard to even find feasible solutions when we're looking at this restoration ordering in these mixed integer problems. On the algorithm side, we're representing here how do you affect the number of repairs you have to consider at once and how that adjusts the difficulty of these problems. One scenario is to be able to use a pre-processing step, in this case the minimum restoration step problem. The objective here is to find the minimum number of repairs that are needed in order to provide full power. So we're only looking at one copy of the network. It's this single time period, much smaller than that full restoration ordering, and then we just select the repairs needed in order to fully supply power, and then we don't have to consider additional repairs that are for redundancy in the network. This is a heuristic. When we take that subset and then solve that restoration ordering sequence using just that subset of repairs, it'll be much easier to solve, but it doesn't represent all those combinations of those non-selected repairs that maybe in a specific order could have restored more power. We'll see an example of that in the case study. But this pre-processing step does significantly speed up the overall solution here, even relative to not doing any pre-processing at all, or comparing not doing any pre-processing to solving both these problems consecutively. Another algorithm we can take a look at is the restoration redispatch. The idea here is that if we can use a lower quality formulation in order to solve restoration ordering, and then recover an AC feasible generator dispatch from that relaxed formulation. This means that we can use a simpler formulation when ordering the repairs and effectively being able to solve it more quickly, but still ensure that the final solution is going to be AC feasible once we fix that restoration sequence. There is potential for some suboptimal repair ordering here because we don't consider all those nuances of the full AC power flow equations, but we can guarantee AC feasibility at the end. And one thing to note is that when solving that generator dispatch problem, because all those repairs are now fixed, all those networks are independent of each other and can be all solved in parallel. And we can also combine these sequences of heuristics and algorithms together. We can take that original network data, solve that minimum restoration set problem in order to get just a subset of repairs. We can order that subset of repairs, and then we can ensure that that final solution is AC feasible using that restoration redispatch. And we can again take a look at the different formulations, power flow formulations that may be used in each of these different steps. So there's a lot of nuance here in how you might want to combine this or have other algorithms that you combine together to get a good quality restoration solution in the end. What this all represents is this trade-off between fidelity and tractability when solving these restoration ordering problems. With the power flows, you can have the AC power flows, which are accurate physics of the actual problem, however, very difficult to solve, or the more tractable linear DC problem, but maybe doesn't quite represent enough of the physics of the network to actually have good solutions in the end, with the second order cone power flow being somewhere in the middle. There is this restoration redispatch of generation, which will allow us to maybe recover a higher quality solution. But then there's also an idea of how many of these repairs are we selecting at once and ordering at once. On the easiest side, the tractable side, is selecting just a subset of repairs. It's this single time period problem, much the easiest thing to solve. There's ordering that subset of repairs, so there's ordering all of the repairs in the problem, which if it comes up to hundreds of repairs, that could be very, very difficult to actually solve. In order to test these algorithms against each other, we have been developing the software package PowerModelsRestoration in the Julia language. It's a software framework for designing and testing these restoration algorithms. It's built off some existing PowerModels framework in the Julia language. What this package has is this mathematical modeling layer for the core restoration tasks. You can select a problem formulation as well as this power flow formulation that you want to use in each of these steps, and then combine these into complex workflows in order to try and have good quality solutions at the end, but still be able to tractably solve them. There is some math to these problems. Here's representation of the restoration ordering problem with the AC power flow, but I don't have time to talk about all of the formulation details of these problems in a 15-minute presentation. I am happy to take questions about it, though. And then on to some of the numerical results that we have. The first is we're going to talk about doing the full restoration ordering problem, and we're going to be comparing across these power flow formulations. We're testing this on the 5-bus network on the left-hand side here, where we consider every single device in this 5-bus network to be damaged. We have some generators, we have some energy storage, and then transmission lines connecting everything. On the right-hand side is a graph of the unserved energy over time. as these repairs are being done. So at the start, we have all of the power in the network, all of that load not being served. And over time, as devices are repaired, that unserved energy is going down. And then after 7 repairs, all of the energy is able to be provided in this network. We bring in the second order cone version or solution in the green here. And you can see that it actually came back with the same solution. There's like barely % error representing the losses in the network, but it's effectively the same ordering sequence that it solved with. This isn't a guarantee by any means with these 2 different power flows, but in this sort of a case of every device being damaged and such a small network, it's not entirely unexpected. When we bring in the AC representation in the blue, what you see is that it has a much higher unserved energy over time. So one first question to ask is, well, were those DC and SOC formulations even AC feasible? And it turns out that when we test those, they were. That restoration sequence was completely AC feasible. The problem here was that the AC formulation was stuck at a locally optimal solution. It wasn't able to actually find this other restoration sequence, still AC feasible, with less energy, unserved energy over time, because it was stuck in these locally optimal solutions. The issue here being that it's nonlinear, non-convex, and you can't get guarantees that the solution you find will be global. Next up, we're taking a look at this minimum restoration set problem as a preprocessor. So selecting that initial subset repairs and ordering that subset in comparison to ordering all of the repairs in the problem. And we'll be showing an example of this using the second order cone power flow formulation. Here we have that same 5-bus network on the left-hand side here, but the dark or the black devices represent ones that were selected by that preprocessor in order to restore these devices. The dashed gray ones are not needed in order to fully supply power in the network. On the right-hand side, you can see in the orange is the same solution for the second order cone restoration ordering problem that we saw 2 slides ago. And then in comparison, we're looking at the blue, where we use that preprocessor to down select the number of considered repairs that are in this problem. What you can see here is that initially this has the same amount of unserved energy going on, but then there's a little bit more total unserved energy. However, it does fully restore power after 6 repairs instead of 7 without that pre-processing step. So it's kind of this trade-off here of like, well, it selected fewer total repairs that were needed, but it did have more total unserved energy because that pre-processing step doesn't consider the ordering of these combinations of repairs that might result in a small amount of unserved energy total. So there's this sort of a trade-off there. Basically, it means that this is a heuristic preprocessor, but one thing to note is that solving both of these problems back to back of that minimum restoration set problem followed by the restoration ordering problem was significantly faster than just solving the restoration ordering problem on the full network. And finally, the restoration redispatch to try and recover a higher quality solution. The example here is with 118 bus network with 10% damaged devices. In the blue was the original restoration ordering solution that we have for the DC power flow, and then in orange we take that same solution and redispatch with AC power flow. You can see here that there's significantly more unserved energy going on, and this is because with that DC power flow it didn't have an accurate estimate of how much power flow it could push or transfer across the network and deliver to loads. Constraints about the voltage magnitude or voltage angles or reactive power flow reduced the amount of power transfer that was possible. In summary, what we're looking at here is these restoration ordering problems that are very large and computationally challenging, and there's this trade-off between fidelity and tractability. With AC power flow, it's hard to even find feasible solutions to these problems. It's very hard to solve. Relaxations like a second order cone might provide good restoration sequence results and capture enough of the physics to still be good feasible solutions. DC power flow doesn't fully capture all the physics, but it might be able to solve that restoration sequence, and then maybe we can recover AC power flow with generator redispatch. And then heuristics may allow us to consider a reduced number of repair decisions and allow us to be able to solve larger networks with these algorithms. The code for this project is available at GitHub at the link below. Thank you.